monotones. We talked there about the relationship. So this is a work that has been done in collaboration with Lorenzo Pieroli, who's nowadays a professor in Bologna, and myself, I'm a senior researcher at TI in Abu Dhabi. Okay, what makes quantum computing magical? I mean, you heard this slide, I think, already 4 or 5 times during this talk, but I'm just going to run through it again in case that's to remind you. So why are we doing this whole quantum computing stuff? So if you want to run a quantum computer and run like on an actual physical quantum computer and want to have error correction, what you normally do is we decompose our unitary. Let's say we want to run Shor's algorithm. We decompose it into Clifford gates and a bunch of non-Clifford gates, for example, T gates. And here the Clifford gates are C0 Hardeman S gate. These are kind of cheap, meaning you can implement them relatively easily on a quantum computer in a Fortran way. But they have no advantage because there's a classical simulation algorithm that can do them efficiently. So alone, they're kind of not practical for quantum computation purposes. So if you want to do something beyond that and actually run a universal quantum, we need some kind of magic ingredient that gives us the power to do non-trivial stuff. And these are, for example, T gates. But you can also use any other non-Clifford gate. But they have the problem that they're kind of expensive because you can't transversely error correct them. So you need to do a more complicated error correction protocol in order to fix these states. So they're basically counting like the T gates kind of, or this magic gives you the main cost of running your quantum computer. So this is kind of the key that will basically take us most of the time. So this is the key quantity that we need to consider and in quantum computing. So now you can ask like, can we somehow weigh magic? Like given, let's say we give them a quantum state or unitary, we just give them like its physical form. And without the circuit, can we somehow tell how magical it is? How far away this is from being just a stabilizer state? How much magic is inside the state? So is there some kind of way how we can measure this? And for this, people put forward the resource theory of quantum computing. And here, basically magic, basically the distance from the set of stabilizer states is kind of seen as the measure of complexity of running a Fortran quantum computer. And here the free states are the stabilizer states, and the free operations are stabilizer operations. And in the first paper from 2014, what was put forward was these 5 conditions, which should be the free operations for stabilizers. So that's running a Clifford unitary, that's a free operation. Then composition with stabilized state, you just take a product state with another stabilized state. This is also a free operation. Measurements in a computational basis. So if you measure like in X, Y, or Z basis, that's free as well. The discarding of qubits, so you do partial trace, that's also for free. You can always throw away qubits. And finally, the 5th one is the above operations conditional on the outcome of measurements. So we perform, let's say, a measurement in a computational basis. Depending whether we get 0 or 1 outcome, you make a different, let's say, unitary operation, a Clifford operation. So this will be also the key point. This will come back again, this point 5. This will become very important later on. And if you now define a monotone, a magic monotone, we consider these 2 conditions, namely it should be 0 if and only if the state is a stabilizer state, and it should be non-increasing under stabilizer operations. Okay, and resource theories, just as a side note, resource theories have been recently, so this is a side note I'm kind of very proud of, so that's why I'm mentioning it. Recently in magic, resource theories have been put in practice for a very important application. So if you checked Twitter and Nature recently, you will find that the Looking Group has run up to 48 encoded logical qubits on their Rydberg atom quantum processor, which has been unprecedented in this kind of scale. And they not only encode logic qubits, but they also put magic. Basically, they run non-trivial, non-Clifford gates in their circuit. And then they basically needed to figure out, like, did they actually create magic? Like, how much magic is in their circuit? And they used basically a resource measure that we introduced recently in PX Quantum to basically quantify how much magic is in their Fortran in their logical qubits. So it's quite useful from, let's say, for example, as an application of certification. So this is just something I wanted to mention because of its recent importance. Okay, but back to the main topic. One issue that we have to deal with is, let's say we want to actually compute a measure, magic monotone or any other resource theory. We have to question like ourselves, how do we actually compute this thing? And if we compute magic monotones, a problem we will often actually deal with is that computing these different measures, let's say like status run, static extent, fidelity, robustness of magic, and so forth. For most of these measures, actually computing this measure in practice will require tomography. So we need to actually compute the density matrix of the state. And secondly, we also require an optimization program, which runs over all the set of all Clifford states, which scales as 2 to the power n squared. So it becomes very large, even for a small number of qubits. And if you do it directly, the limit is normally 5 qubits. So then you're pretty much, this space is simply too large. So it means this is very difficult to actually compute magic in a practical sense, both numerically as well as analytically. It's quite a challenge. And that's why people will propose the stabilizer entropy by the group of Hammer recently, where they basically said, let's quantify magic by considering the Pauli operators, identity, sigma x, sigma y, and sigma z, and consider the Pauli strings, which are just tensor products of Paulis. And then we consider the set of 4 to the power n Pauli strings. So we take all the Paulis that can exist over big N qubits. And then we note that the square of the Pauli expectation value, so we take our state psi, we compute the Pauli expectation value n squared, then we sum over all Paulis, we find something that is proportional to a constant. So if you will normalize it, it will be equal to 1. So you can interpret now this thing as a probability distribution. So basically the distribution of Pauli expectation value squared is a probability distribution. And we now can consider the kind of the alpha moment of this distribution of Pauli expectation values, which make up the alpha Renyi stabilizer entropy. And this measure here is simply you take the distribution psi squared, but you don't take the second power, but you take some power alpha instead, 2 alpha. And this really gives you kind of the moment of the distribution. And one can see that this is a measure of non-stabilizerness. So it will be 0 only if the state is a pure stabilizer state. And it's non-increasing, or in fact, it's invariant under Clifford unitaries. So it seems to fulfill some of the condition of non-stabilizerness, and it doesn't require any tomography or optimization. So you can directly compute it and even efficiently measure it. And yes, so this has been quite useful. So it even allows for analytic computation, as you've seen yesterday by a talk on magic hypergraph states. And you can see why this works well is because stellar states have this neat property that the distribution of Paulis is kind of the most peak distribution, like it has the lowest entropy. In particular, the expectation value of Pauli square is either 0 or 1 for any pure stabilizer state. For example, if you consider the plus state, it will be either 0, or for the sigma x operator, it will be exactly 1. If you take something which is magical, you get a distribution which is more broad. For example, for the T state, you find that the distribution is now 1/2 for both sigma x and sigma y. So the distribution kind of gets broader. And basically this quantifies now how much magic is in your quantum state. Okay, and this has been only proposed 2 years ago, but has already found quite an incredible application where people are studying now the relationship of this stabilizer entropy with other measures. So I just compiled this incomplete list of people where they applied it. Just to give you a few examples, it has been applied to study the magic of many-body physics efficiently for MPS. I will discuss this in the next slide. And there's also a poster by Salvatore. You can check this out today again during the poster session if you haven't done it yesterday. You can efficiently measure the experiment. This will be the next talk by Subin, so she will talk about this. And you can also use it to bound other measures of non-stabilizerness. I will also comment on that. And I just want to make some mentions. It's very important in relation to pseudonymous. The talk by Keisha Bharti was mentioned this shortly on this topic on Monday. And something I just want to highlight because I found it quite unusual. Non-stabilizerness is related to the noise robustness of shadow tomography. So if you do shadow tomography, how robust is your shadow tomography to applied noise is depending on the stabilizer entropy, surprisingly. So I found this quite surprising that this is the case. Okay, so I will now mention some of the points of our on a recent paper in quantum with Lorenzo Piroli. First, we showed how to efficiently compute the stabilizer entropy for matrix product states. So just to mention, matrix product state is a way of representing states, quantum states on a classical computer with whenever the state has a low entanglement cost, which is characterized by this factor chi. So chi is the bond dimension. You can think of it being just the bipartite entanglement of the state system. And we showed there is an efficient algorithm whenever this alpha of the Renyi entropy is an integer at greater 1. You can compute it like this with the scaling. And we show that for the case alpha equal 1, one can do a kind of Monte Carlo sampling approach. And you get an algorithm that scales quite well with chi to the power 3. So this is quite practical. You can go to easily to hundreds of qubits in like 1 dimensions on the order of 1,000. And you can, like, for example, study like many physics, like you study the Heisenberg ground state, but you can apply this to quite varied different topics of many-body physics and do interesting studies there and how magic evolves, let's say, as a function at closed-loop phase transitions. Another application is we found there's an important relationship of stabilizer entropy with other magic monotones. These monotones you already heard before in the previous talks. Just to mention, there's the min relative entropy. You can think of being as the log of the stabilizer fidelity, the max relative entropy, the log of stabilizer extent, and the log free robustness of magic. And we show there is that the stabilizer entropy is a lower bound in all these measures. So you can establish this neat hierarchy that goes from the log free robustness to the max relative entropy, min relative entropy, and the stabilizer entropy. So they're all have this nice relationship. And we also conjecture there's an upper bound for the min relative entropy, so the stabilizer fidelity. So it's not only lower bounded, but we also conjecture there will be an upper bound with this factor here. So this is quite nice because then basically both upper and lower bound will basically kind of squish them together, and you can kind of use them to get estimate on the min relative entropy, which alone is quite difficult to complicate to estimate because you have to run an optimization problem over the set of stabilizer states, which is numerically quite difficult. And for the case alpha greater 1/2 of the stabilizer entropy, we rule out the existence of any lower bound that is independent of the number of qubits. So this is not possible to establish a lower bound. Okay, so I'm going to come about to the relation between stabilizer entropy and magic monotones. So if you remember, in the beginning I shortly discussed like what is the main condition of being a stabilizer, being a magic monotone. And the question now is, does the stabilizer entropy actually fulfill all these conditions here? So it's 0 only for stabilizer states, and it's non-increasing under stabilizer operation with all these 4 or 5 points here. So before addressing this question, I first asked existing literature, and you find several papers that say the stabilizer entropy is indeed a magic monotone in different publications that come out recently. I also asked ChatGPT, and also ChatGPT says indeed the stabilizer entropy is a magic monotone. But I thought like maybe I should have a closer look, and okay, we can check. So let's just check one by one. Okay, if you check, we find of course one problem that has been already noticed in the first paper. It's non-zero for mixed stabilizer state. So if you put not a pure stabilizer state, but a mixed stabilizer state, something on the convex hull, it's a convex combination of stabilizer states, you'll find it's non-zero. That's okay. I mean, this is a property that many resource measures have, that they only valid for pure states, for example, the attainment entropy. So we can just restrict ourselves to pure states only and pure operations. With operations that map pure states to other pure states. And if we now do this restriction, then I'll consider, okay, we now live only in the space of pure states and pure operations. Is it still a monotone in this case? Okay, so we're going to check. It's invariant under Clifford unitaries. Units, of course, are pure, and you know that stabilizer entropy is invariant under Clifford, so this is fine. If you composition with a stabilizer state, a pure stabilizer state, it will be non-increasing, so that's also fine. If you do a measurement on a computational basis, it will also not increase. If we discard qubits and we consider only partial traces that result in a pure state at the end, for example, we just trace out a product state, it's non-increasing as well. And the final problem is the fifth question. So let's say we apply any of these operations condition on the outcome of measurements. So the fifth case is it's not clear a priori. So now we can basically consider what about measurements, and we consider now the case of adaptive Cliffords. So meaning we run a Clifford operation, let's say Hadamard and Synod in this case, and then we apply a measurement on, let's say, the first qubit. And then depending on the measurement outcome, we choose a different operation. So let's say if you get outcome 0, we do nothing, and if you get outcome 1, we apply a Hadamard gate. So this would be an adaptive Clifford circuit. But depending on the measurement outcome, we choose a different unitary operation. So we can now ask, is this a monotone in this case? And it turns out it is not the case. So we can find an explicit counterexample whenever alpha is smaller than 1 of the Renyi entropy. So we take this initial state, which has 4 qubits, and we found this via numerical optimization. So you can find this example here, and we now measure in a computational basis. Basically, we measure 1 qubit, and if the outcome is 1, we do nothing, and the outcome is 0, we apply the following unitary, some kind of Clifford operation, and we get this final state here. Then we compute basically the difference in magic between the initial state and the final state, and we found this delta m here, difference is negative, meaning after doing this operation, this Clifford operation, the magic actually increases. So we get more magic after the Clifford operation. So meaning this is a direct violation of monotonicity whenever alpha is smaller than 2. So we can find this. If we go, so meaning this fifth condition is not true. And under this fifth condition, it is not a magic monotone, even if you only consider pure operations. We find that if alpha is greater or equal than 2, we get no violation anymore for this state. And we also checked extensively for other states and couldn't find any counterexample. So what's with this case alpha greater or equal than 2? It's not clear. So it may be a monotone or not a monotone, but this is an open problem for which we do not have an answer yet. Okay, we can also consider a second property called strong monotonicity. So this is not one of the original 5 conditions that was set previously in the initial paper. So this is something you not necessarily need for a monotone. But it's a nice property to have because it means that basically what it means, strong monotonicity means is that if you apply a measurement in a combination basis on let's say the first qubit, and then you get an outcome state and you renormalize it such that it becomes a normalized state again, and you compute its magic. Then you average over all possible outcomes. So it's kind of like you look at the magic on average on a basis measurement. And basically demand that magic should not increase. So it's a strong monotone, it will not increase under this kind of operation. And this is of course relevant only when experimentally actually flag the state outcome. So you don't actually consider you don't average over the outcomes, but you kind of track each outcome individually. So you do some kind of post-selection on the outcomes, or you track them individually and don't take the mixed ensemble over them. So if you now consider this case, for alpha smaller than 2, we trivially find that strong monotonicity is violated because already monotonicity is violated. But what's with the case alpha greater or equal than 2? So if we check this case, we can find that strong monotonicity is also violated. But in this case, it's very different. So the states that we use to violate strong monotonicity for alpha smaller than 2 doesn't work. It will be fine. It won't have strong monotonicity. But if we consider now a different set of states, then we consider the stabilizer state, the 0 state, and we consider the magic state, the T state. They have very different magic, right? The stabilizer state has 0 magic, the T state has a lot of magic on the order of n number of qubits. Now we consider kind of a perturbed state. So we have mostly a stabilizer state plus a small epsilon perturbation with a magic state, where epsilon is small. And if we check now the magic of this perturbed state, we find it's constant. So it scales only with epsilon squared, but in particular, it's independent of the magic of the state. So although there's now basically a contribution which is highly stabilizer and a contribution which is highly magical, the resulting state is independent of the number of qubits. So it has some magic that is independent, just scaling with epsilon squared, but doesn't scale with the number of qubits whenever alpha is greater than 1. And now we can show that if this is the case, you check now the state and you make a projective measurement on the first qubit and you post-select for the outcome 1. And you find the resulting state has a magic now which scales linearly with n, right? Because you basically post-select mostly for this state. So you find the resulting state will basically scale with the number of qubits. And this means, of course, implies that if you make the number of qubits large enough, eventually will violate strong monotonicity whenever alpha greater than 1. Meaning strong monotonicity is both violated for any alpha for the stabilizer entropy, for the Renyi stabilizer entropy. Just as a side note, since we didn't find this in literature, the min relative to the magic, so the log of the stabilizer fidelity, is also not a strong monotone. So basically, find whenever the stabilizer entropy violates the monotonicity for alpha greater than 2, alpha greater than 1. The same is the case also for the stabilizer, for the min relative entropy. So they behave the same way. They both violate strong monotonicity for the same type of states. So they seem to be quite closely related in that regard. Okay, so that basically sums up the problem we seem to struggle with here. If you want to compute a magic resource theory, as to our knowledge, we either have to do tomography and optimization, which is kind of annoying, or we have to sacrifice our strong monotonicity. So basically we have to choose. Do you want to have like something which is a strong monotone? Then we have to do tomography optimization, or if you want to do something efficiently, we have to sacrifice something apparently. So this seems to be the current conundrum, but maybe there's a way out, I don't know. Okay, so I already come now to the conclusion. So basically I showed that the standard entropy has a very wide application. So it's surprisingly connected across various fields beyond in quantum computing and beyond. And it can be efficiently computed, which is quite useful from a practical point of sense, and has application even in running on quantum computers. But it seems to be not a monotone, and the measurements are double Cliffords for the case alpha smaller than 2, and it's not a strong monotone for any alpha. Okay, the question that remains is, can we somehow prove or disprove the monotonicity for the case alpha greater or equal to 2? So this would be a very important address. That would help a lot. Then the question is, can we somehow recover the strong monotonicity? And there's a possible explanation that Subin will talk about. It's possible maybe to do it by sacrificing the additivity property of the Renyi stabilizer entropy. It may be possible to recover the strong monotonicity condition. And finally, it would be very nice to prove this upper bound, because this would mean that the stabilizer entropy is a kind of both upper and lower bound of the minimum entropy, and kind of an efficient approximator of this important magic monotone. So it would be quite good to show this relationship, to use it in practice as a kind of approximation of other measures of magic. All right, with this I conclude, and I thank you very much for your attention.
Nice talk. Any questions? On the violation of the monotonicity with alpha less than 2, how to find your counterexample? I have no intuition on this complicated state. What property this state have?
So you mean this state here for alpha smaller than
this initial state.
Yeah. Honestly, I don't have a good intuition either. It seems to be like related to the Pauli spectrum. So it has like a very kind of unusual distribution in the Pauli space. So I think one can look at this and characterize it. But yeah, to be honest, like how we found it is by doing numerical optimization. So we tried to basically run an optimization program and try to basically find a violation of this condition here. And then eventually we found this state. Okay, but I agree, this is quite an interesting state. So it looks very unusual and has this unusual property. So maybe that is relevant. So it seems to be a very ordered state. So maybe it's also useful for something else. I don't know. So maybe it has some deeper meaning. It would be quite interesting to explore this.
Okay, thank you very much. Okay.
Yeah, like the mean relative entropy, actually, if you just look at the stabilizer fidelity without the log, that would be strong anti-monotone.
Yes. Okay.
So yeah, so without the log, so like in entanglement theory, what they do is 1 minus stabilizer fidelity, and there convexity and strong monotonicity going in the right way. So like for any monotone based on a divergence, there is a way to build a convex and strong monotone. So it's
yeah, thank you very much. Yeah, I didn't mention, but yeah, I absolutely agree. Like it's the log that caused the issues here. So if you like status fidelity itself, is like you just show by basic conditions what the minimum relative entropy are, it must satisfy strong monotonicity. So yeah, just the log kind of puts everything in disarray. I think for the log of the robustness matching and the log of the stability, they still appear to be strong monotones, I think. So it seems only be an issue in this case with the logarithm.
So one more question. Any further questions for Tobias? Okay, so if no, let's thanks Tobias again for the nice talk.